So just a few more examples of these homogeneous differentials. Let's go ahead and take a look at this y fifth derivative minus 8 fourth derivative plus 16 third derivative is 0. Characteristic equation, pretty easy. M to the fifth minus 8m to the fourth plus 16m cubed equals 0. We could factor out an m cubed and be left with m squared minus 8m plus 16 equals 0. And then we can factor the remaining trinomial as m minus 4 squared. So now that we know this, we can clearly see that there are two solutions that are different. However, there's actually a number of solutions that are the same. So notice that m cubed is going to have a multiplicity of 3. So m1 equals m2 equals m3 equals 0. And then m4 equals m5 equals 4. And again, that has a multiplicity of 2 because of the square. So here's how we're going to write the solution to this. Now we have two sets of distinguished roots, right? So what we're going to do is we're going to say y at x is going to be equal to c1e to the 0x, because that's our solution, plus c2x e to the 0x for the first repeated root, plus c3x squared e to the 0x, right? So each time we're just increasing the power of x by 1. Right? Now we're going to start over because of the 4 has a different solution. So we're going to say plus c4 e to the 4x, and then because there's one repeated root, plus c5x e to the 4x. Of course, another way to write this very easily, y at x is going to be equal to c1 plus c2x plus c3x squared plus c4 e to the 4x plus c5x e to the 4x. Right? And that would be our solution. If you want to check that, find the third, fourth, and fifth derivative and stick it back into the original differential. Of course, that would be fairly taxing, so it might just be best to believe that you have the correct answer. Now this is one that we haven't looked at yet. So we have, or a type we haven't looked at, although it looks pretty innocent, y double prime minus 6y plus 25y, 6y prime plus 25y equals 0. And then we have these initial conditions. So here's what we're going to do. We're going to set up the characteristic equation, m squared minus 6m plus 25 equals 0. And unfortunately, we can't factor that. So we're going to have to use our quadratic equation. Or quadratic formula, excuse me. So a is equal to 1, b is equal to negative 6, and c is equal to 25. And we're going to throw that into the quadratic formula. So m is going to equal to the opposite of negative 6, plus or minus the square root of negative 6 squared minus 4 times 1 times 25. And then we're going to divide all of that by 2 times 1. By computation, we get 100 minus 36, which is, or 36 minus 100, which is negative 64, divided by 2. And then clearly we're going to have a case 3, because when we simplify this, that becomes 6 plus minus 8i divided by 2, or in other words, 3 plus minus 4i. All right. This means, because we have a complex solution, that we have a case 3. And recall that case 3 says that the solution y at x is going to be equal to e to the ax times c1 cos bx plus c2 sine bx. And I'm going to put those in parentheses so we understand that the angle bx is part of the trig function. Well, in this case, a is 3 and b is 4. We just worry about the absolute value. We don't worry about the plus or minus. So A is the real part, B is the complex part. And so for us, y at x is going to be e to the 3x times c1 cos times 4x plus c2 sine of 4x. All right. Now, unfortunately, this is an initial value problem. So we need to figure out the derivative. And you might notice that to find the derivative, it's going to be a product rule. All right, because we have a function of x and then another function of x inside. All right. Now, fortunately, we have 0 as the initial value for x. So it's going to make it a little bit easier. But let's go ahead and find the derivative. So y prime of x is going to be equal to 3e to the 3x. And the rest of it's going to stay the same. And then we're going to add to that, we're going to keep the e to the 3x the same. The derivative of cos 4x is negative 4 sine 4x by using our chain rule. The derivative of sine 4x is going to be 4 cos 4x. All right. Now we are going to substitute 0, and we're going to substitute 1 and 3, so 3 and 1 respectively. So this is going to become 3, this is going to become 1, and all the other x's are going to become zeros. So I'm just going to substitute that right away and get our system. So we're going to have 3 is equal to e to the 0. Now e to the 0 is going to be 1. We have c1 cos of 0. So c1 times cos of 0 is 1. And then c2 sine of 0, and sine of 0 is 0. Right? So that actually makes it really easy. I'll worry about that in the end. And then we have 1 is going to be equal to 3 times 1. Okay, because that e to the 3x is going to go away. c1 cos 4x, so that's going to be c1 times 1 plus c2 times 0 plus 1 times negative 4 c1 times 0 plus 4 c2. Right? So again, all I did was substitute 0 back in for everything. Right? I'm going to need just a little bit more space, so let's go ahead and find that. Right? Clearly, we get that 3 equals c1 for the first. This goes away, and we get that 1 equals 3c1 plus 4c2. That becomes 9. 9 minus, or 1 minus 9 is negative 8. So this just becomes negative 8 is going to be 4c2, or in other words, negative 2 equals c2. So now we can go ahead and write the final solution to this by substituting back in for c1 and c2. We have 3 and negative 2. So our y of x is going to be equal to e to the 3x. We said that c1 was 3, so that's 3 cos of 4x. And then we had minus 2 sine of 4x. So this should be the solution to our initial value problem. One final example, and this one is a little bit sneaky by the way it looks. So we have y triple prime minus y double prime minus 4y is equal to 0. All right. So we're going to have to start by using the characteristic equation, just like we've done with the other 5 problems. So that's going to be m cubed minus m squared. And I'm just going to put in a plus 0m minus 4 is equal to 0. we can't factor this. So we have to go all the way back and remember that there is a trick to being able to do these. And the trick is that we just try to find a solution by plugging in numbers that we think are going to work. All right, now I know that 1's not going to work because 1 minus 4 is negative 4. What about 2? Well, if m equals 2, that means we're going to get 8 minus 4 minus 4, which is indeed equal to 0. So m equals 2 is a solution. M minus 2 equals 0 is a factor. And just like we did before, what we're going to have to do is we are going to have to do long division. If you're missing any powers, make sure to plug those in with a 0. All right? Otherwise, when you do the long division, it might not be as easy. So we're going to do our long division. M minus 2, m cubed minus m squared plus 0m minus 4. What multiplies by m to give us m cubed? M squared. M squared times m cubed, m cubed squared times negative 2, negative 2m squared. We flip the signs around, and we wind up with m squared plus 0m minus 4. Now we're going to do it again. So what multiplies by m to give us m squared? Well, that should just be m. So we're going to add an m into this. That's a plus. Let me erase it so it looks like a real plus, or as close as possible. M times m, m squared. M times negative 2, negative 2m. And again, we're going to flip the signs around. So we get 2m minus 4. What multiplies by m to give us 2m? That's going to be 2. Right. So 2 times m, 2m. 2 times negative 2, negative 4. Flip the signs around, and we do indeed get 0. All right, so now we've reduced the order of the polynomial by factoring, which is exactly what we wanted. And so I'm going to have to move down just a little bit. And now we get a new characteristic equation that's been reduced. We get m minus 2, m squared plus m plus 2 is equal to 0. Unfortunately, we cannot factor the quadratic at this point. So just like we did before, we're relegated to looking at the quadratic formula. A is 1, B is 1, C is 2. And so when we substitute into the quadratic formula, minus 1 plus or minus the square root of 1 squared minus 4 times 1 times 2, all divided by 2 times 1. It's not as nice of an answer as we got before. Negative 1 plus or minus the square root of negative 7 over 2. And so what we end up with is negative 1/2 plus minus root 7i over 2. And so right away we can see that A is a minus 1/2, B is root 7 over 2. Okay, so it's not a nice answer, but that's okay. We can still get to our solution. Now notice that that's the complex roots, but we also have a real root. Remember that we had m equals 2. All right, so that's going to be a real root, which is a case 1, and then these two are going to be the case 3's. So this is our case 3, this is our case 1, and we're almost done with this. So let's put it all together. Y at x is going to be equal to c1 e to the 2x plus, and now we're going to use that case 3. So that's going to be e to the minus 1/2 x, because that's a, c2 cos root 7 over 2x plus c3 sine root 7 over 2x. All right. Unfortunately, it's not an initial value problem. We can't really simplify it any further. So this is going to be our solution whether we like it or not. So hopefully this takes care of all the homogeneous types of differential equations of second order or even higher order. Now we're going to learn two techniques before our first examination to be able to solve non-homogeneous second order differentials, and they still have constant coefficients, so we're not going to worry about variable coefficients yet. So suggestion might be to make sure you're good with this section before you move on to the next one, because everything that we've done in this section we're going to have to do every single time that we solve a non-homogeneous differential.